called your rigidity modulus. And finally, for your three-dimensional object, whether it's expanding, let's say a cube is getting contracted or it's getting expanded. Actually, it doesn't matter. The change in its dimension to stress was given as what here? Bulk modulus. Now, these are the three quantities or three constants that you all will be dealing with. So previously, we found a relation between a linear strain and your different. Like the shearing strain is basically for your two-dimensional object. We found that it was your phi was 2e. And for a bulk, it was how much? It was the volume strain was 3e. Now the change in the volume is proportional to what? Is equal to 3 times. Now it will depend on your dimension. This is your one-dimensional object and this is your three-dimensional. So three-dimensional roughly goes like this with 3 and this is your two-dimensional. So roughly it goes like 2. So apart from that, what we were doing was we started doing relation between each modular. Relation between each moduli. And apart from that, now suppose if we apply certain amount of force, which we were doing previously, or we applied a uniform force in three perpendicular directions. This was Q, P was acting over here, and P was acting actually, the force is applied on three mutually perpendicular direction. That will be sufficient actually. That will start expanding it uniformly in all the side. And which is coming outside is R, and which is going outside is also R. Basically what we are doing is we have a cube and we started expanding it around three mutually perpendicular direction. So what will happen? Initially it was like this, then it will expand on this direction, it will expand on this direction, and it will expand on this direction, which is sufficient because it seems like it's being expanded uniformly. So that's why we will be applying three certain stresses on three different directions, mutually perpendicular. Basically means perpendicular to each other. Basically x, y, and z axis. In this three mutually perpendicular axes, we are applying certain amount of force. So that's why this cube will become large. So suppose if we apply a force along this cube, if we apply force along this cube, what will happen? Let's just take this side of the face. Okay, let's call it A, B, C, D, E, F, G, and H. Let's just consider ABCD. Let's just consider ABCD. Just for your reference, I'm doing. Actually, the force will be applied to the whole body. Now, if you will see, initially it was of this side, A, B, C, D. Now you are applying Q over here. Now what will happen? It will get deformed. Then it will be something like this actually. It will get elongated. Initially it was of this side and it has changed to this. It was A, B, C, and D. Initially it was of this. Now simultaneously if the force is applied on this direction, it will get elongated across CD. It will get elongated elongated along this direction, but simultaneously it will get contracted in this direction as well. So that's why we will be defining two quantities. One is elongation. Now we'll be considering two lambda. Let's say lambda is extension per unit stress. Basically what this means is, if you apply a unit stress, or let's say 1 Newton per meter square force, a unit stress along Q, then what will happen? The extension will be, the change will be exactly the amount of change. This extension will be how much? Will be lambda. That is basically this. Now simultaneously it's getting contracted over here across A and C. That will be defining as what? Mu. Mu is basically what? Contraction per unit stress. Now what does that mean? If you apply 1 Newton of stress along Q, it will get contracted in this direction. It will get contracted in this direction, which is basically what? Mu. Now these are the two quantities that we'll be requiring. Now one more thing which you all will notice is, if you apply a force across this Q along CD, then the contraction exactly occurs perpendicular to that direction. If you are applying force across this direction, the contraction is coming at what? At perpendicular to this direction. As you can see clearly, because you are applying force in this direction, the contraction is happening in this direction. Now it's occurring in this direction, in this direction. So these are mutually perpendicular. Can you see these are mutually perpendicular?
Yes, sir.
So the elongation will occur in the direction of a force applied, and the contraction will be occur on perpendicular direction. Now let's say a P across elongation. Let's consider elongation across P. So what will be the elongation across P? You are applying your stress of P along P direction, then it will be what? Lambda times P. Is this point clear? Why it will be lambda times P? The elongation will be, because if P is 1, it will be simply lambda. Now you are applying certain amount of stress, which is P across, then it will be lambda times P. Clear? Now simultaneously a contraction will occur across mutually perpendicular to this P, which are basically your Q and what? R. As I have shown, because if you apply in the three-dimensional object, if you apply a force across this, it will get elongated in this direction, but simultaneously it will get contracted over here and also over here. Clear? Is this point clear?
Sir. Yes, sir.
As you can clearly see from this, it will get elongated, it get contracted. But if you look at this side of the face also, if you apply force across, because this will get stretched out, so it will be slightly smaller. Is this point clear? So
Yes, sir. Yes, sir.
contraction will occur on Q and P, which is basically mu times Q and mu times R. This is the total amount of contraction which will occur. So the net elongation will be what? Net elongation will be how much? Will be elongation across P minus the contraction, which will be basically lambda times P minus mu of Q plus mu of R. This is your net elongation across P. Now similarly, net elongation across Q will be how much? net elongation across Q will be simply, this will be what? Q, and this will be P plus mu R. So similarly, net elongation across R will be how much? Lambda R minus mu of P plus mu of Q. I think it's clear till here. Till now, do you have any doubts?
No, sir.
Any doubt? Okay. Now let's consider one case. When we apply stress along P, only along P, let's say. When we apply stress only along P, basically that means your Q and R will be 0. As we are applying stress only across P, it will get elongated in this direction. So we are not applying any stress along Q and P. So the linear strain will be, linear strain, which is basically a net elongation, okay? This is basically a net elongation. Sorry, the linear strain will be what? Your net elongation will be lambda times P. Actually, it will be what? Over here, it will be same as your net elongation because the cube is of unit side. Let's consider the cube is of unit side. Because the strain is defined as what? Change in dimension, which is your net elongation, which is lambda times P divided by our original length, which is your unit length 1. So it will be lambda times P. So this is your linear strain. So the Young's modulus will be defined by what? Young's modulus is basically a stress by strain. This is given by E. Stress is how much stress was over there? P. And strain is how much? Lambda by P. So PP will cancel out. So you are left with 1 by lambda. This is basically a Young's modulus. Now let's consider, this is your first case. Let's consider the second case. Now this is, we consider R as 0 and P equal to negative Q. Now this is the kind of force, let's say, kind of stress which we are applying over here is, basically R was going over here, this, no force is acting or no stress is along this direction, and P is acting on this direction, and Q is also acting where? In this direction, but what? The direction is opposite. Can you see? The magnitude is equal but opposite. So it will come like this. Clear? So actually this will come like this. Because the P is acting on this direction, if you consider this direction, it will come on this direction. Is this point clear or not? Is this point clear?
Yes, sir.
Yes, sir.
I think.
Yes, sir.
If you have any doubt, you can just interrupt me in between. Now let's say direction of P is in this direction. So obviously, what is the opposite of this? Opposite of this is basically this arrow. So that should come in Q. Initially, Q was acting like this. Initially, Q was acting something like this. Now, opposite to this will be what? Opposite to that will be this. This is basically Q. So that's why Q will be, now Q will act as a steering. Now you can exactly see it's acting tangential to this plane. Then the net elongation across P will be net elongation across P will be how much? You are still lambda times p plus, actually it was minus mu q plus mu r. Actually it was something like this. So the net elongation will, or basically you can write this as strain itself. Lambda p r is 0, mu is negative p, and this is 0. So you are left with what? Lambda p plus mu p. P you can take it out common, lambda plus mu p. This is here net elongation. Now from here you can see what? This is basically a net elongation, or E. Now we have a certain relation with the angle of shear. The angle of shear, because this force is acting in this direction, so there will be what? Certain angle which will be sitting over here, because it will get elongated in this direction. So this angle is basically your phi. So the angle of strain, we have relation for this, which is E is given by, or sorry, phi is given by twice of E. We'll be using that over here. So the angle of shear, or phi, will be how much? Phi will be E, will put it over here, which is lambda plus mu times of P. This is basically what? Your angle of shear. Now the rigidity modulus is given by what? Rigidity modulus is given by what? The angle of shear, which is basically a change in dimension, phi by stress, which is Q. Sorry, Q by stress by strain. Actually, it should be. So it will be P. Sorry, P or Q. P by phi. So which is basically P divided by twice lambda plus mu times of P. This 2P will cancel out. So you are left with what? So this is for your rigidity modulus, which is given by a Z. This is your relation for your rigidity modulus. Now finally we are trying to find a relationship between each moduli. So first we got Young's, now you got rigidity, and finally we are left with your bulk modulus. Now let's consider the case where we are applying P is equal to Q equal to R. When all of the forces or all of the stresses are equal, so it will expand uniformly. So the net elongation will be again, elongation will be how much? Basically lambda times P minus, I think one of the relation will be sufficient, Q plus mu times of R. But you can see all of the quantities are same, so we will be setting all of them as P. So from here you can see lambda minus twice mu P, you can take it out common. This is your net elongation. This is basically your E. And we know in terms of your bulk modulus, or in terms of your three-dimensional object, here for your bulk strain, will be given by what? Or basically your volume strain or bulk strain should, I think previously you used volume. So volume strain is given by 3 times of E, which will be basically how much? 3 times of lambda minus twice mu times P. Now we'll find the bulk modulus. So the bulk modulus, this is given by what? G will be how much? Stress by strain. Stress is P, strain is 3 lambda minus twice mu of P. Both of the P will cancel out, so you are left with what? 1 by 3 lambda minus twice of mu. This is basically your bulk modulus. So now we have a certain relationship between all of this, because all of them now contain a simple 2 variables, which is basically your mu and lambda. So I will just summarize all of this result over here. For your Young's modulus, you got E equal to 1 by lambda. For rigidity modulus, you got G is equals to 1 by twice of lambda plus mu. And from here, K, you got what? Sorry, this was G, and this was K. The mole modulus was given by K, I believe. I think let's put it K. I think we used G previously. So K was given as what? 1 by, let's use it from here, 1 by 3 lambda minus twice of mu. Now these are the three relationship. By using this relationship, we'll get what? A relationship between E, G, and F. So till now, do you have any questions? So we are going to stop over here. Till now, if you have any questions, you can ask now.
So
Any
we can
questions?
take lambda also, mu also, anything, right, sir?
And you can take anything. That is just A, B, C, D, or anything you want. Basically, that is what? Stress per unit length or per unit
24.
elongation, actually. Elongation per unit stress, actually, that is. So any other questions? Any other questions?
No, sir.
Okay, then we are going to stop here.